This is what dance feels like. Nice.
It seems that the microphone is working.
Yeah. Okay.
So, welcome to this afternoon session. It's now 16:15:07, and I have the pleasure of introducing Richard Johansson, who is from Gothenburg University, who is an expert in making computers understand what we mean when we talk to them, or something like that. Please welcome.
Thank you. So I was apparently putting in the programming languages session, but this will be not about, well, Prolog or Haskell, but human languages. A little bit of Python, but, well, not about programming languages in general. So the talk is called Learning the Meaning of Words from Text. So I'll start by reflecting on what we actually mean when we say that the word has some sort of meaning. And since I'm concerned with building computer software that tries to understand the meaning of text, we need to think of how can a computer have a notion of word meaning. Then we will move on to the main point of this talk, which will be how can we discover the meaning of a word automatically. For instance, how can a computer learn to know what is the meaning of the word pizza, for instance. And then finally, well, I assume there will be some nice party tonight, but if you feel like hacking instead of going to the party, I will provide you with some links to some software that you can try out. And this will be free software, of course. So a few words about myself. I work here, not in this building, but in the building next door at the Department of Swedish Language. So I mainly teach. I occasionally do a bit of research. And my topic is natural language processing, that is computer programs that extract information from text. So if you're interested in this topic, we have a master program if you would like to pursue a career in this field. So if you're interested, just Google for MLT and GU. And the application deadline is in April for EU students and in January if you're international. So so the talk is about the meaning of words, but what we actually mean when we say that a word has a meaning. So naively, when we say that humans understand, we typically have something like this in mind. A human will hear something said, for instance, a green tree, and then some sort of mental image will be formed in the head of this person. So if you speak to philosophers, of course they will say that this model is terribly naive, but let's work with that now because it's something that we can relate to. So if we want to build computer programs that understand the text in some very mechanical sense of that word, what would that mental image be? So if we want to build software that has some sort of meaning notion, then we need to say that the word pizza, for instance, has some sort of meaning. So we need to kind of connect this string to some representation of what the word pizza means. What is that thing that we say that we have the string pizza, and the pizza refers to some concept, but what is the concept? So let's consider what would we do as programmers. So I guess most of you hackers would start by making an, well, depending on your education, but probably you would do something like making an object-oriented model of the things that you're interested in. So for instance, we can, oops. Okay, before we go to the object-oriented model, let's consider what does the dictionary say about pizzas. So a dictionary, this is the Collins Dictionary of English, it says that a pizza is a dish of Italian origin considering of a baked dish, and then there are some ingredients. So this is a kind of informal definition of a pizza. But of course, as a computer cannot work with this because it's unstructured. So let's go back to what I said previously. We will do some object-oriented model. So let's do a UML diagram, for instance. So we will have a class called pizza, and the class pizza will inherit from the class food, and there are also other kinds of food, for instance, sushi. So then when we say that a word has a meaning, we say that the meaning of this string pizza is the class that is also called pizza. So now we have some little model of word meaning. Of course, this is a bit limited, so I mean, compared to all the knowledge that you have in your heads. So let's add more classes. So we have, and this is of course just the beginning. We can say that pizza is a kind of baked food, and the sushi is a kind of cold food, and food in itself is a physical thing. So we can do this endlessly. Also, still this object-oriented model is more limited than that textual definition that I had previously, because so we have basically covered the first part of saying that a pizza is a kind of baked food. But then there were also other information in the dictionary entry, for instance, that there are tomatoes and cheese on the pizza. So we will need to add tomato and cheese to the object-oriented model, and then we will have need to have more relations than just inheritance. We will say that the pizza has some cheese in it and tomato. Okay, so what we are basically doing now is that we are making something that computer scientists would call an ontology. And when people say ontologies, they are typically huge compared to this little toy example that I have shown now. So some of you might be familiar with ontologies. For instance, how many here have heard of DBpedia, for instance? None of you? Okay. So how many of you have heard about Word? Okay, you have heard about Word. Okay. So let's just very briefly look at this. So Word, for instance, is a structured dictionary, basically. So, no, download search, use Word. So if I just ask WordNet what is a pizza, I will, first of all, I will have a definition, but then I will have superclasses, which in WordNet will be called hyperlinks. So pizza is a kind of dish, which is in turn a food, which in the end is a physical thing. Then there are other ontologies like DBpedia. So DBpedia is basically Wikipedia converted into a structure. So in Wikipedia there is a lot of structural information, such as there is an info box saying that Stockholm is the capital of Sweden. So there is a lot of information in Wikipedia that has kind of a structure, so you can imagine that you can convert this information into a database. So that is DBpedia. The final link here is called Iago, and Iago is a bit like DBpedia, but they have also tried to merge it with many other knowledge libraries. So here is, for instance, the Iago entry from Gothenburg. So it's a kind of entity in a database, and then there are typed links to other entities. For instance, we can say that the person Adam Johansson, which is then also an entry in this ontology, has a link to the entity Gothenburg because Adam Johansson was born in Gothenburg. Okay, so this is then a kind of definition. What is the meaning of the word Gothenburg? But so here's the catch: these resources, are very limited. So I mean, if you imagine the effort of building such a thing by hand, it will of course take you a lot of time. So in DBpedia and Iago, they have saved time by using semi-automatic methods, by, for instance, parsing the Wikipedia info boxes. But still, these are limited. Well, and partly because, there's so much specialized knowledge that the ontology builders don't know, and there are new words coming in, and so on. So these are limited. So because of that, there is an interest recently in developing methods to automatically discover meaning from text only, and no, let's say, knowledge engineering, no ontology building. So these methods require a lot of text typically, but text is fairly accessible compared to, let's say, structured ontologies. So, I mean, in this case, you can actually go home after this talk and try it out, while if you would build an ontology, it would take you years. So before we say how this actually is done, I need to introduce another notion, that is the notion of word space. So in a word space, each word is connected to something called a vector, which I guess you know what it is if you have some, let's say, technical background. But basically, a vector is a point in a coordinate system or an array of numbers. So here is an example of two-dimensional meaning vectors for a number of words. So we can see here that pizza and sushi are near each other in this word space. So this means then that they are kind of similar words. These are words with fairly similar meaning. So the word spaces will typically have many dimensions. Depending on how you do it, they can be between, let's say, 50 dimensions up to many thousands or even more dimensions. But now when I draw them on the screen, they will be two-dimensional, so that we can kind of intuitively reason about them. So how can we then, what is the actual information contained here? So instead of this very structured information that we have in the ontologies, we have some intuitive notion of similarity. So in the word space, similarity is defined by geometry. So as I already said, I think that pizza and sushi are kind of similar because they are near each other on the screen in this case. And so pizza and sushi are much more similar than, for instance, pizza is to router or touchpad. So and this then corresponds to the, let's say, distance in centimeters in this case, but well, in general we will use the Pythagorean theorem or something to compute it. There is also the other intuition that if we say that this is a coordinate system, we put the origin here, then we will look at the angle. So pizza and sushi are similar because the angle between them is very small. Okay, so we have this intuitive notion of being similar, but we don't have the, let's say, detailed structure that we had in the hand-built ontology. We know that pizza and sushi are somehow similar, but we don't know that they are similar because they are both a kind of food. So we will come back to this idea later on. Yes, and of course we can kind of argue about what does it mean to be similar, because well, a pizza, I say that pizza and sushi are similar because we can eat them, but some other guy might say that pizza and touchpad are similar because both are flat. So I mean, it's kind of informal definition of similarity. But so what's the point of doing something like this? So there are several applications, and one kind of obvious thing is to use similarities in search engine. So for instance, if I Google for pizza in Gothenburg, probably I want to eat. So then it's okay to give documents that contain the word calzone, for instance, but not documents that contain the word router. And this is true of many other kind of natural language processing software. For instance, if I have some crawler that wants to find mentions of company names, then if I tell it that Spotfire is the name of a company, and then I see some other string, for instance, Tokamatic, which is a company here in Gothenburg, but I haven't told it anything about Tokamatic. But I see from the word space that Tokamatic is extremely similar to Spotfire. So that might give me a reason to conclude that Tokamatic is also a company. So this is useful for natural language processing software. So how could this then work? So when people talk about word spaces, there is a cliche that always must be said, and I will say it now as well, which is you should know a word by the company it keeps. And it was said by an English linguist called Firth. And what this means is that two words probably mean about the same thing if they appear in similar contexts. So what does that mean? For instance, if two words tend to appear in the same set of documents, then they are probably similar in some sense. Or if they have the same words around them. Or we might even be really creative and try to use the images which are around them. But this is an open research problem, as I will say later. So for instance, if I say, I eat a pizza, I eat some sushi. So they are similar because we tend to say that we eat these things. So let's look, for instance, what are the verbs that we would use with cakes and with pizzas. So cake, we would eat it, we would bake it, we would even throw it. This actually occurs in text. I mean, when people throw cakes at Bill Gates, for instance. A pizza we would eat, we would bake it, we would order it, cut it, and so on. And basically the things that we do with pizzas. So as you see, the kind of frequency, well, I haven't shown the frequencies, but the distribution of words that appear around mentions of cakes and of pizza, they are similar. So this is basically how we would make these vectors in the word space. So if we say that each of these word occurrences will correspond to one dimension in the vector space, then we have then we can convert pizza into a vector. So I will show. I'm sorry about this Swedish. Some of you might understand Swedish. So here is the corresponding words in Swedish, and in this case I actually have the frequency counts. So we have eat and bake for both of these words. And so now we could take those frequencies and make them into vectors. So this is a fairly intuitive approach how to make the vectors. Recently there is a kind of hype around these vectors, and this is mainly because of developments in new algorithms how to make the vectors. So, for instance, Nikolov at Google has something called the skip-gram model, which is basically we make a statistical model that can kind of guess a word that is left out. So we would use some machine learning to predict what is the word here. So can anyone guess what is the word here? Any ideas? I think probably all of you have some sort of idea what it is. Well, maybe not exactly, but I think you all know what kind of thing I'm looking for.
Vienna?
So,
Vienna?
Vienna? No, it's not Vienna. It's Paris actually. So, but never mind. Okay, so as a byproduct of this statistical model, a word space will be made, and the property of this is that when we have similar contexts, we will get similar vectors. So it could be Vienna, but it's Paris. So Paris and Vienna will be very similar. Okay, so this method leads to fairly high quality vectors if we evaluate how well they work. So I said previously that in the word spaces we have only the kind of notion of things being similar in a very informal way, but actually it was discovered fairly recently, last year actually, that there is more than just similarity. So there is actually some sort of structure. So we said the ontologies have structures, but the spaces do not. but there is actually some structure that is kind of implicitly encoded. So it was actually the same person at Google who discovered that we can use these spaces to answer kind of analogy questions. So for instance, if I had this test, give me the x such that Moscow is to Russia as Stockholm is to x. So what is this x? Of course, it's Sweden. So, here is a demo where we can test something like this. So, for instance, we might test. The pan is to sushi, as you say, is to what? What will come? What will Americans eat? Burgers. Okay. Yes, burgers. So, and yes, of course we can play around with this endlessly. So what does Swedes eat, for instance?
Meatballs.
Let's see what the web thinks. Swedish meatballs. Okay, I'm not gonna annoy you more with this, but I will take another example that my students showed me. So if we say that Sweden is to ABBA as Austria is to what?
Conchita. Conchita Wurst.
Well, that's a good guess, but actually it's the von Trapp family from Southern Okay, so I think they are kind of similar to ABBA. Okay, so yeah, so here is the link. I will try to put these slides online so that you can test it for yourself. Okay, so if we look at it a bit more analytically, what this shows is that the word spaces have some let's say regularities. So if we look at, for instance, male and female words such as king and queen, prince and princess, and so on, they're kind of nicely lined up in a fairly nicely structured way. So to answer these analogy questions that I had previously, if I say that prince is to princess as king is to x, I would kind of subtract prince and princess and then add it to king, and then I would arrive here to queen. So to answer these analogy questions, we just do, let's say, very, very stupid vector arithmetic. So it's fairly interesting that such a stupid idea can actually work. And if we look at countries and cities, then we see a similar thing. This is from Swedish text. I have done this figure where the previous one was done by Nikolov. So here are some countries with capitals in Swedish, and we see that they are also kind of nicely lined up. So okay, it looks a bit like black magic, but it's not. So if we actually think, how could such a thing work? So imagine that we are speaking about Moscow and Russia, for instance. So we can say I went to Moscow and I had a lot of vodka. I went to Russia and I had a lot of vodka. So actually Moscow and Russia could be similar in some sense, but then of course there are also other things like the parliament in Moscow, the parliament in Stockholm. So Stockholm and Moscow are similar in some other dimension, let's say. So that is why we get this nice arrangement. So then to the software. So Nikolov, this person at Google who came up with this idea, he has packaged the algorithm into a software called Word2Vec. So this is free software, so that you can download. So, and if you go to the web page of this software, there is also there is also a pre-made model that was done at Google using a lot of news text from Google. So, so if you don't want to build a statistical model yourself, then you can use that. So that is a C program. So there is also a very nice Python library that is called Johansson, which was implemented by another Czech person. I don't know what Czechs also into this, so I'm not going to pronounce the name. So this is actually a Python implementation of Nikolau's algorithm, and it's a very optimized implementation. So it's not exactly as fast as the C implementation, but it's still quite usable actually. So it's built in something called Cython, which is a kind of glue between C and Python. So this includes the word-to-vec algorithm, but also several other useful algorithms. And if you would like to go even more low level, if you would like to build vector processing things in general, there are many libraries. I mean, because now we enter, let's say, mathematics territory, so there are numerical libraries, I guess, for all languages. So for Python, there is NumPy. Well, I'm not going to list all these, but most of them have the linear, some old Fortran code in the, let's say, bottom. Finally, the software that I used to make the images in this talk were done with scikit-learn, which is a machine learning library in general, but in this case I just used that to project out to 2 dimensions. And then I used another Python library called matplotlib to actually plot. Okay, so if you want to use this at home, then you of course also need text. I mean, if you don't use Google's pre-trained model, so then you need text. So how do we get text? So it depends on what language you're interested in. So Wikipedia is always a good option. Because that is fairly large for many languages, and also some languages which don't have much text in other contexts. Of course, there are differences in how much text we have in Wikipedia. For English, for instance, English is of course the biggest Wikipedia. Swedish is also quite large. I guess German are also large, but then if we go down to more exotic languages, the Wikipedias are small. And then if you're using Wikipedia, you need to kind of take away all the, let's say, wiki structure if you're just interested in the text. So that would be the, let's say, all the boilerplates, categories and that stuff, and the wiki markup. So if you're interested in some of the big European languages, then we have a project called Web as a Corpus, which is done in Bolzano in Italy. So, so they actually crawled a fairly large amount of text in English, French, German, and Italian. And for English, if you go to the word-to-vec web page, there are some pointers to text collections in English that you can use. So for Swedish, I can make some self-promotion. So the Department of Swedish collects a lot of text. What is nice about our collections is that we have many different types of text. But well, increasingly, the text that we have are from social media. So it's a kind of asymmetric sample of text. So I'm not sure how many Swedes we have here, but I think the biggest of our collection comes from a social media website called Flashback, which is very weird. Yes, fringe political, those kinds of people. Okay, so if you're interested in our text, you just need to take away the XML, and then you have raw text. So we have, because when you process text, you need to do some massage. I mean, you need to split into sentences and split into words. But that has already been done with our text. So you just take away the XML and then you have the text. So here is how you would use Johansson, the Python library, you can go to this web page and see how it could be used. But it's very simple. You would just, I guess the hard part is what I have left out, how to get the sentences and how to pre-process them. But assume that we have some sentences, then we just use the word2vec class. And then it will build a statistical model for typically, well, a day or so. Well, it depends on how much text you use, and of course how powerful your computer is, and some tuning of the algorithms. So then you can, when it's done, you can query it. What is? Give me the thing that is to king as man is to woman. So then it would output queen, for instance. Or you can just give the most similar word to king. Okay, so before we end, I should like to say something about some open research problems in this area, because this is a very hot topic in research. But there are many things that are not solved yet. And I would say for the problems that I list here, there are probably people working on them, but there is no, let's say, satisfactory solution. So for instance, what if we are interested in Turkish? The words are very complex. They consist of many small parts, so we get huge words. And also if we look at the vocabulary of possible words will be huge. So here is one word, for instance, that means, was it from those that were in our garbage cans? So a single word that means that. So if we try to build word spaces like I described, it will not work very well. There is some research on how to connect words and the images that are associated with them in text. Or we could even imagine that we try to kind of interact with the world, for instance in a robot or something, that we have some sense of readings. Can we build word spaces so that the word dog in English has the same vector or a very similar vector to the Swedish word hund, for instance, which means dog in Swedish. And that would be useful in many multilingual applications, for instance, machine translation. Another open research problem is what can we do about words which have more than one meaning? For instance, if we take the word rock, so it has two meanings in English, and in this case it has two meanings in Swedish as well. So the two different meanings of rock are in Swedish. One is rock music and the other one is a coat. So can we build word spaces that kind of break apart the word vector for rock and make two different vectors? So I have currently a student who is working on that problem. So that is what I had to say. So I'll try to see if the organizers can put this presentation online so that you can get the links. Otherwise, if you want to ask questions over email, I'm happy to answer. Okay, thank you all.
So thank you very much, Rico. Are there any questions from the audience?
Yeah, are you doing any text-to-speech translation in Swedish or something?
I don't know. Well, I guess there are. Well, I think certainly there are companies who have good, let's say, speech recognition and speech generation. I'm not an expert in that particular field, but I'm fairly certain that there is.
Okay, thank you. So how are these word spaces built? Because you said they have 50, 100, 10,000.
Yes.
They're not in
Okay.
two-dimensional. So
you saw the logical gap. Because I said that typically the word spaces have 50 to, well, a few thousand dimensions. And then a few slides later, I said something like, let's make one dimension for each word that occurs around it. But then I guess the word space would have, well, if the vocabulary has 50,000 words, then we would have 50,000 dimensions. So typically they are smaller. And that is because typically if we build them this way, we would apply a mathematical operation called a dimensionality reduction. So
my question would be, what does the dimension stand for? What is the meaning?
So in the original way that I built this particular word space, one dimension would be, let's say, a word that this likes to appear with. So for instance, there would be one dimension for the word eat. So a pizza and a cake would both have a kind of high value of the dimension for corresponding to eat. So yeah, for instance, if I take the Swedish word frequencies, you see that if I convert all these frequencies into dimensions, then they would be, both of these would have a high value of the eat dimension. Okay, so this is kind of simple, but then, as I said, in practice we will convert this big matrix into a small matrix. So we do something called a dimensionality reduction. And the problem then, of course, is then the individual dimensions are not interpretable anymore. So for instance, if we just have this simple two-dimensional coordinate system, of course I cannot say anything what is the meaning of this dimension or this dimension. I mean, we can say that, okay, this dimension is foodness, but I mean, what does it mean? So I wouldn't say when we go to low dimensional spaces, the dimensions don't really have any meaning anymore, except to provide the, let's say, similarities.
It might be related to meaning of dimension, but I wanted to ask about garbage words. We have prepositions and things like this in language, but those are not words in these.
Well, I would say it depends on how what you do actually. So I think that some people, when they count, where did I have that example? Some people, when they count, they would just take away the stop words, the words that don't provide any information.
Yeah, but also when I saw that people who works in topic modeling usually gets a class of topic with garbage.
Yes, so I think that it depends very much on what we will use the spaces for. So, okay, now I'm going into a tangent, but if we want the kind of space to reflect the topic, then we would have, we would look at the whole document and we would probably take away the stop word. But if we are, let's say, interested in a word space that, so that words are similar, if they have very similar grammatical behavior, then we probably don't take away the stop words. We would use what you call the garbage words. I mean, it's very informative if it has a preposition just before it. So it depends very much on what we're using it for.
Any more questions? There's one over there.
What methods do you use to test your idea?
That's a very important question, actually. It's an extremely important question. Because as I said, I mean, what does it mean for two words to be similar? So I said that pizza and sushi are kind of similar. So, okay. So this can be done in two different ways. So first, if I say that I want my word space to be arranged so that similar words are near each other in the space. So then I can have a benchmark where humans have said how similar they think that two words are. So we ask users how similar is a pizza to a sushi. So then they would say, okay, 6 on a scale from 1 to 10. And how similar is a pizza to a cake? Okay, maybe 8. But well, it's still kind of, I mean, what is the meaning of this number? So I think this is kind of shaky. The second approach is, I mean, so I said that these things are useful because we can use it in, let's say, search engine or in some application, and I guess the most objective way to test this is just to use it in an application list and see which one works best.
I'm wondering if there is any database, any standard database where people use to
Yes.
as benchmark. For example, I know that for summarization, there are like 1,000 texts and ask people to summarize the text.
So
100 summarization for a single text, and then they compare it. They compare the machine summarization with those summarization.
So of course, if you're testing it in an application, it depends on what the application is. But if you just care about similarity in itself, then there are tests that, just like I said. So there is something called WordSync 353 or something like that. So it's exactly what I said. We'll say that pizza and sushi have a number of 6. So then for the second thing that I told you about, Moscow is to Russia, Stockholm is to X, Google has released their own test set. So it contains questions like this, and I don't remember exactly what they are, but they are. I think this type of question is included with countries and capitals, and also the let's say gender words. So we will have analogies like these words.
WordNet, are you using WordNet when building the workspaces?
Well, my students will eventually do that, but I don't know. I don't think many people have done that, but we plan to do it actually. But of course it's
because WordNet and the ontology, it's not only what is in WordNet, it is also all the reasoning that you can do, and then you get more information on the ontology.
I think that the two approaches are complementary and they should absolutely be combined.
So unfortunately we're running out of time, sort of, and unfortunately as well, it's unfortunate that the model takes so long to crunch. It would have been nice to know what the flashback crowd thinks of FSCONS, what we're similar to. But probably, or something similar. Commies or I don't know, hippies probably. Anyway, thank you very much. Let's thank the speaker again. And that concludes the penultimate part of this track. Next and last but not least is Zijan Ali, who will talk about Bala, which is a new programming language used within the GNOME community. That will be in 15 minutes. So if you're interested in that, please stick around.
Jag har lyckats wastea this year.